Good morning, everybody. I am Calderara Simone. I will talk about directional statistics and pattern recognition techniques for human surveillance. My tutor is Professor Rita Cucchiara. My co-tutor is Professor Andrea Prati. When we talk about human surveillance, we talk about the process of extracting, detecting, and classifying human activities and events in a specific scene. This problem is definitely complex because the scene can be complex itself and evolves in time, and the range of activity is pretty vast. One possible solution is CCD cameras to capture the data for the classification. In particular, when we use a camera sensor to acquire the data, we talk about human video surveillance. This process is the process of acquire and classifying visual cues to obtain a deep understanding of the scene. The first example of automatic human video surveillance system was the P-Finder system in 1997 that detects and tracks human in a controlled room. The first example of outdoor automatic video surveillance system was presented in 2000 and was the W4 system by Larry Davis et al. And detect, tracks, and classify human action in an outdoor environment. When we talk about human video surveillance, this process mainly involves two different senses. The first one is computer vision. That's a branch of artificial intelligence and image processing concerned with computer processing of images from the real world. And in particular, the problems that are related to human video surveillance are the motion analysis, for example, people segmentation and tracking, the geometry reconstruction that involves 3D vision or camera field of view registration, and feature extraction in general. That in the case of video footage could be, for example, people position, pixel intensity, or color properties. And could be used for event detection, such as smoke detection in video streams, face recognition and people identification, or human action classification in general and behavior analysis. The other science that's involved in human video surveillance system is pattern recognition. That means the imposition of identity on input data, such as, in our cases, images, by the recognition and delineation of pattern it contains and their relationships. In particular, when we talk about human video surveillance, we can talk about model learning. For example, learn the model by samples. In the case of PDF, this is about all the parameter learning techniques, such as the EM or variational techniques, or in the case of non-parametric PDF, the kernel density estimator. Could be classification, so in the case of human video surveillance, we can talk about, for example, people trajectory classification or behavior analysis in general. And this process could be done with general pattern recognition classifiers, such as the SVM or Bayesian network in general. And when we analyze video streams, time is an important use, so we must have a model to handle sequential data. So in the case of pattern recognition techniques for sequential data, we are talking about predicted model for time-varying data. So in the case of tracking, we are talking about Kalman filter and particle filtering. Or for example, people activity analysis, we are talking about dynamic Bayesian network or HMN. So let's see a brief scheme of a video surveillance system. On the top row, we have the cameras that could be, for example, fixed or moving. The first stage is about extracting the object of interest from video, and this process is called segmentation. After that, the object must be tracked in time on each video footage, and this process is called tracking. If we have several cameras, we may be interested in fusing together data acquired from different sensors, and this process is called consistent labeling, or more properly, data fusion. After that, we can perform some high-level reasoning on the data, for example, behavior analysis or posture classification, or in the case we are analyzing face tracking or face identification for privacy concerns or identification purposes. So the existing image lab solution previous to my PhD were a system for moving object segmentation a system for shadow analysis and a tracking system. And related to the high-level reasoning, a system for posture analysis and face detection. During my PhD, I've studied all the 3 stages of the processing chain of a video surveillance system. And in particular, first I developed a robust background model for segmentation using computer vision technique for color analysis and intensity gradient analysis. This is an example of the system. On the top left corner, there's the input video. On the top right, the extracted object. And on the bottom left, the extracted human. Subsequently, I studied the problem of fusing data coming from multiple cameras, and I used both computer vision techniques for camera field of view registration and pattern recognition for projecting people identities across camera streams. This is an example of the system working in front of faculty, where people sharing the same color shares the same identity on all the 3 cameras. So, for example, we can see the red person on both cameras and the orange one. Sorry for the color spot. And subsequently, I studied the smoke detection, the event detection in outdoor environment, and in particular the smoke detection using pattern recognition technique. And I've studied the image energy decay using a mixture of Gaussian and a kernel density estimator to detect smoke in outdoor scene using a CCD cameras. Once the smoke is triggered, it is marked in blue and tracked in the scene. I also studied behavior analysis using both computer vision and pattern recognition, and in particular the trajectory shape analysis for video surveillance in outdoor environment. And I used computer vision technique to project trajectory onto the ground plane, so to obtain a projection invariant representation of trajectories, and pattern recognition technique for sequential data analysis involving circular statistics and sequential data analysis for comparing trajectory shape. This is an example of the system working in a public park on Reggio Emilia. And the system is able to mark abnormal trajectories online, signaling it like in that case. Subsequently, I studied the problem of people activity analysis using computer vision technique to extract basic features for the analysis that are the motion history images, and the same pattern recognition technique I use for trajectory analysis. In particular, we can see on the left throughout 3 different videos of people performing different actions, and on the right we transform this action in a unique signature that is characteristic of the action. The system is able to analyze this signature as a trajectory and then classify the action. Now I will talk about what I think is the most interesting contribution of my 3 years PhD, and this the use of directional statistics for trajectory shape analysis. The problem is trajectory shape analysis, so analyze trajectory shape despite their position. The feature we choose were sequence of angles, and the techniques belong to pattern recognition and are the use of circular statistics, EEM algorithm, dynamic programming, and K-methods clustering. So the problem we said before is classifying trajectory according to their shape. So we are not interested in the position, but trajectory having the same shape must belong to the same cluster. And trajectory having different shape must be treated differently by the system. So usually trajectory are described as sequence of coordinates in some plane, for example x and y or I and j in the image plane. But we prefer to use an angular representation because it's definitely more compact, it is monodimensional, and allow us to classify the shape without taking into account the position. So we compute the angle between 2 subsequent points, and we then obtain a sequence of angle instead of a sequence of coordinates. After that, the system first analyzes the principal component of each trajectories using a EM algorithm, then map each sequence of angles to a sequence of PDF, each one belonging to the main component of the trajectory itself, and then sequences of PDF are compared using an alignment-based technique to attain a similarity measure between two sequences. The novelties aspect are the use of circular statistics for human surveillance. We will use a distribution that is circularly defined, so it is periodic and is definitely a proper model for angular data. We derive the EM algorithm for this specific distribution. We derive a proper distance to compare two probability functions in a closed form. And we use the global alignment technique to compare sequences of data that may vary in length. So when the variables are angles, usually linear models are inappropriate, for example, Gaussian or mixture of Gaussian. If we think about two different angular observations, one, for example, at 1 degree and the other one at 359 degrees, and we take the mean will be 180 degrees. And this is obviously wrong because the mean should be around 0. So we must adopt a model that takes into account that the feature we are using is periodic. And we choose the von Mises distribution that is circularly defined, so we can see the cosine at the exponential. And this distribution can wrap after a period of 2p. Similarly to mixture of Gaussian, we define the mixture of von Mises as a weighted sum of von Mises distribution, and we use that distribution to model the data belonging to a trajectory. So a single trajectory is modeled as a sequence of angles, and then principal component of the trajectories are extracting using the EM clustering algorithm on the sequence of angles. So after that process, we have several von Mises distribution, each one with its weight, that represent the principal direction that are present in a specific trajectory. Well, for sake of completeness, I report the updated equation of the EM, but then each trajectory is mapped from a sequence of angles to a sequence of PDF using a maximum a posteriori approach, where each angle is linked to the mixture component that's most similar. After that, we have a sequence of PDF that must be compared. These sequences may vary in length, so we need a measure that don't strictly depend on trajectory length. So we choose to use a global alignment technique, that is a technique borrowed by informatics, and it is used to compare DNA sequences. We also use dynamic programming to speed up the comparison process and obtain real-time performances. So how the alignment works? Well, two sequences are put one on the others, and spaces may be inserted in the beginning, in the end, or in the middle, since we obtained the best alignment. After the best alignment is obtained, the distance between two sequences is the symbol-to-symbol distance. In our case, symbols are PDF, so we must define a measure to compare two PDF, and in particular case, two von Mises PDF. So we decided to use a statistic distance because it preserves the circular properties of the PDF itself, and we derived the closed form of the Bhattacharya coefficient in the case of von Mises distribution. When the distance is computed, we can use this measure, for example, for clustering data. In our case, we use the K-Medoid clustering algorithm, and each prototype of the cluster is the element that minimizes the sum of intra-class distances. One common problem when using these K-type clustering algorithms is define the number of clusters. So in our cases, we use an iterative procedure where in the initialization step, each trajectory is a cluster center itself, and then we fuse together cluster centers that are close enough till convergence. The testing phase was performed using the learn and predict paradigm. That means that the knowledge is continuously updated when new data arrives. So first, when we have a new trajectory, we compare it with existing methods, then we can perform classification. If close enough to a cluster, it is assigned to a cluster and then classified. If far from all the clusters acquired during the training set, new clusters are created and priors and clusters weight adjusted. So the tests were performed on both synthetic and real data and evaluate in terms of classification accuracy and normal abnormal accuracy, where an abnormal trajectory is a trajectory that is infrequent in the training set. So if we take a quick look at the performance, the system has an accuracy of about 97% in case of real data and close to 100%, 99.6% in case of synthetic data. They are pretty less noisy. And we compared our method with an existing HMM-based approach that is pretty used in literature, and we outperform it as well. Concluding, we propose a model for angular sequences analysis. We derive the EM for mixture of circular for Mises distribution and the Battaglia coefficient to compare to unimodel for Mises distribution. So the model we propose is general enough to be applied in several contexts. For example, for people action analysis or for text analysis in multimedia application. The work was accepted as oral in IEEE conference on computer vision and pattern recognition, and now we submitted it to PEMI. In conclusion, during my PhD, I performed an holistic analysis of the human surveillance processing chains, and I applied the synergy of both pattern recognition and computer vision technique to propose some, I hope, interesting solution to common video surveillance problem. And finally, we propose a new framework and some algorithms for sequences of angular and linear data analysis. I worked in that project. The international one is the BSAFE project funded by NATO, and in particular I worked on behavior analysis and trajectory shape analysis. The national one are the FreeSurf project funded by Italian Mure, and the Leica project. And for the smoke detection system, I collaborate with the Bridge 129 company. This is a list of my publication. I have 3 journals. One international ceramics journal where I have applied pattern recognition techniques for ceramic surface analysis, and computer vision and image understanding and PAMI on consistent labeling problem. I have book chapter on multi-camera people analysis using pattern recognition techniques, and several conferences. That's it. Thank you.